In this video, my goal is to give you a really brief foundational discussion about Fourier transformation and the interferometer. These equipment and techniques became really useful for all kinds of spectroscopy. Some of the main benefit could be the operation time for you to get the data. It takes much less time, and also because we can repeat the experiment multiple times in fraction of seconds, we can do thousands of experiments in such a short time. Therefore, we can improve the signal to noise ratio. Therefore, that allows us to work with a very diluted sample and very small amount of sample. We live in 21st century, yet much volume of the textbooks teaching with the concept of instrument from the age of continuous wave. CW light source. I might do that too because it's conceptually teaching us how the fundamental physics is actually helping us to discover the properties of chemicals. So when the light source is emitting a variety of the wavelength of your choice of the bulbs, depends on what you want to study, like we discussed before. We used to have a prism that can split the wavelength, or we can use movable small mirror gratings, or you can call it wavelength selector. So the instrument, as you turn dial or the click on the software, these things move, and we know what wavelength is actually going through the sample. And then even after going through the sample, you can have them to purify the wavelength. And then the light come into the detector, and in the detector, the photon turned into the electricity, and the intensity of the electricity, the amount of the electron that's get detected by the detector, will be simply plot out, as the machine knows what wavelength is coming in now, and that's giving this much of the electric power. Irrelevant to that, when they are selecting other frequency after passing through sample, that wavelength is being producing this much of electricity. And that's how we used to get the spectrum. But with the technological development, we have all kinds of resources, such as a laser. Laser is able to generate a broadband signal, and then we are able to have the sample interact with all kinds of wavelength at once. And then using the interferometer, you can deconvolute. You basically figure out what wavelength of the light is present, and then what intensity of each frequency is present. Then we can plot them out. And during the process, you can utilize Fourier transformation, the mathematical manipulation. This mathematical description that can interconvert from the function of the frequency to the function of the time, or vice versa. And here again, I'm not trying to give you explicit mathematical manipulation, but I'm just trying to make a point. It's not quite complex. It's conceptually simple enough if you keep practicing. Anyway, so we can conceptually see the waves in the frequency based or time based. So again, when the traditional continuous wave light bulb is generating all kinds of wavelength of light, and that will be selected using monochromator, and then the light will be interacting with the matter, and the matter, as we discussed, has all kinds of frequencies. And then when a certain wavelength of light is given at a time, this let them interact, and that let it interact with the matter. So each cases you have some changes on each photon at a time, and then this will be detected by detector. So when machine is giving this wavelength selectively, and it will be detected because we know the frequency, we just plot out the intensity, and same for the more shorter wavelength light with a high energy. And again, and then the usefulness of the Fourier transformation has been known for a while, but due to the technical problem, it wasn't actually made applied for actual field science. But passing 1950s and 60s, mini computers became available, and the fiber optics came in the handy, and then laser became popular that can emit the broadband light sources. So they all came in one place, and now we are enjoying these great FT machines. So all of these lights hit the molecule and resonate with the frequency existing in the molecule, and then change the photons coming out, and then go through interferometer, generating this interferogram. Then you can see this is the function of time. So as the interfered light going through the space, the detector see the changes of the light intensity, and that is the ferrogram you got, and that is the function of time. But we need to plot out in the frequency. There we needed Fourier transformation, and we do it. Then we get the function for frequency, and because these graphs are a function, we can also calculate the area under this curve by doing integration mathematically, and we have a better way of making the graphs more useful or clear, and the manipulations became much convenient, easier, and the much extensive application we can have these days. So these signals, if you compare, this used to be just measure of certain electricity. Now this is mathematical function. These are like graphs that we get these days out of the computer. So I think it's time to talk about interferometer. Here is the schematics of it. I hope you can connect this new drawing with the previous drawing. You have a laser sample, the little box I showed you for interferometer, and then the detector. You can change and arrange the location of the detector anywhere you want using a couple of mirrors, so it doesn't matter. Now I have a detector down here to give you more insightful understanding. Then you do Fourier transformation after that, and then data processors plotting that out. And this little box can be actually, you know, can be as small as a big cell phone. And then also, interferometer doesn't have to have moving mirrors. There's so many different types of interferometers. Depends on your goal. It basically is making coherent output, and you can measure all kinds of informations like length and size, like as big as a galaxy. And you can look at the surface. If you deal with the light, this can be very useful. And again, in learning concept, the traditional primitive one is making more sense for us and you as a student. So let's try understand what happens inside. In the diagram, you see 3 mirrors. This mirror with the full reflective surface is fixed. The distance is precisely measured to the half mirror with the low density of the silver on it. So half of the light will be reflected, but the other half will go through. Okay, and there you have a third mirror that is actually moving back and forth. It used to move like a 10 to 30 centimeter, but these days, like I said, it can be as small, and you don't have to have a moving mirror. So it all really depends. So originally, say this laser is emitting one type of wavelength, okay? For the easiness of getting the understanding. So certain wavelength of intensity going through the sample, then whether it's absorbed or not, the intensity will change. But wavelength, let's say, remains the same. It doesn't have to, but say it remains the same. And then the light will be, without changing the phase, will hit the mirror and then go this way, half of it. And then the mirror will make it come back. Then if this moving mirror is right at the same distance as this, okay, if it is, then same thing happens, and then when they come back, they start interfere. Okay, I'll talk about interference down here, but it will interfere and generate this new interfered light, and that will be detected. Okay, so that signal here is called the interferogram, and that we need to apply Fourier transformation to convert that time domain function to the frequency domain function for us to apply the value to the physical model better, so we understand the chemical structure better. Okay, let's say we are considering at the moment, although you have 3 waves shown, this red wave and the black wave that we can describe with the sine function, right? With a different intensity or same intensity, it depends. But let's just say you have the general formula like this with a angular speed and the time, so that's the angle. And if you have a phase difference, then you can use different theta value, but here you have a same value for the sake of easy understanding. Say you are making these 2 lights interacting right here at the mirror, okay, to generate the interferogram. So the interference taking place, and you heard about constructive and destructive, but those are too extreme, and we'll have to apply to the partial interference, right? But let's just say you have photon wave 1 and the 2 interfere, then what happens is you have a twice intense light with the same frequency. So if this is y1 and the 2, basically they are the same thing, right? Then the outcome will have same frequency but twice intensity. If they are same intensity twice, but if they have a different intensity, simply add them up. Well, if you have to interfere with light 3 that has a completely opposite phase, the opposite phase will have interference that's destructive. So if you add them up, you have, say, exact same intensity, the amplitude, then you'll cancel and it becomes 0, right? But if they're not exactly same, it ended up making the wave weaker. That's when you have a same wavelength. So with the same frequency, you make it intense or dimmer. Those are the two ways of thinking of the interferogram. Here, this is when you have two same intensity and frequency waves, black one and the red one. You know, black and red. Oh, black and red, black and red. Try to interfere at different phase. Okay, same phase, opposite phase, slightly and more different phases. So outcome wave function, as we saw before, constructively depends on their relative intensity, but you know, we assume they're same. And here you got completely destructive interference. But as you have a more and more phase difference, the intensity gets weaker and weaker. Okay. So here, when you have the red and the black photons split and get combined, generated interferogram, as you have the mirror moving towards or away from the half mirror, this is what's happening. Therefore, if you plot the intensity of that frequency of photon, right? When the moving mirror is at the same distance, the intensity of the interferogram, you know, this photon coming out after interference, will be intense. As you move in or out either direction, the intensity decrease. If you move more, they decrease. If you use Mathematica and actually put different degree angle in the formula we had before, and then try to make them interfere, you'll see the drop is very significant, you know, something like that. So what happened is, though, whatever the intensity was, right, the frequency information of the photon is now spread in the space in centimeter. So frequency, the secret of the photon, is presented in the space. And then this distance is always, as you can see, velocity times time. So this you can consider at the same velocity of the moving mirror. Time is domain. That's almost same as the distance domain. So you have a wave function in time domain. That's the wave you get as an interferogram. So this, okay, this interferogram is time domain function you got. And then you can do this many times in a couple of minutes, thousands of times. However, when we run spectroscopy, we are using multiple photons, right? With a different wavelength. So these are the wave numbers. In 1 centimeter, this wave has 2 waves. This has 5 waves in 1 centimeter, so more frequency. This unit is used for IR. And if you allow them to interfere, that's what you get. I know my drawing is not in the right scale, but what it meant to be is like this is identical to this, okay? And then I hope you can see the new frequency came out, because they have what difference in the phase. So when difference increase, you know, beginning is the same, but difference is increasing this way, and then it goes down dramatically, the intensity, and then when it comes back up, they start to get same phase, for example, start to go up. So it has another wave information coming from the difference of the phase of the 2 photons. And that's what the detector is detecting. Then this wave function will be Fourier transformed from the time domain function to the frequency domain function. Then you get 2 peaks because you had 2 signals. Remember, that's the one coming out of the sample, so they may not have the same intensity. You know, there could be variations of it, but this Fourier transformations are able to catch that and it able to show different intensity at the different frequency. Now we are ready to correlate each frequency with the materialistic model, the molecular structure. If you Fourier transform only this, obviously you get 1 signal. And same manner, if you only Fourier transform this, you get 1 frequency. Mix them up and you get 2. And you mix a lot of different wavelength lights. Then the red is the interferogram. Okay, that's when you have some. And in our NMR machine, you have what? Photons in the range of 4,000 to 400. If you run UV spec, you run from 200 nanometer to 400, sometimes 700 nanometers. Depends on how you set. You have ways of mixing different band of the lights. So you come up with the pure interferogram of the light source as a blank. So when we run instrumentation, we always run blank first. So if you zoom in this area, you still see many different waves, you know, just like this or that, but more complicated because you have so many waves mixed up. But near the mirror, having same distance from the fixed mirror, you have a most intensity, but as the mirror go closer or away, you know, symmetrically the intensity decrease. But inside of this, you see little spikes, and that will be eventually be able to transform into many original wavelengths. Okay, then when this blank interferogram is interacting with the matter, some of the vibrations will be absorbed to excite some modes of vibrations that's active in the spectroscopy that you are running. Then the interferogram that is missing certain photon after absorption or get weakened, getting partially absorbed, your interferogram will be changing something like this. And you can see some more blank and then less cancellations, making this line a little more rough and visible. And same over here. And that we know by just looking at that, oh, something is absorbed. We don't know too much, but if you Fourier transform of this, then you get to have many peaks. We don't know, but we'll get to that later in specific spectroscopy. But we'll be able to come up with many waves that's absorbed after Fourier transformation. I hope this helps you to understand spectroscopy better if you are pursuing graduate level of degree. This will come in handy to start studying at the graduate level. Here is the traditional laser setup. This best thing about this is like in our 1990s, we can build a computer kind of model. You have the laser coming through this, and you have a mirror splits, and half of the light coming into this mirror. Fix the mirror I talked about, and then lights going back. And then you can change the distance here using the knob here. Very, precisely you can control. You have a very precise reading from here. And then go back, and interference happening. And then this is not a detector, but for this simple experiments, they're trying to see the interference of the circular things on the screen as a detector. Such as this, when lights off in the room. Also, you can build your own customized system if you need to observe something of your own. And this come in this small size as well. This is something like other type of interferometer coming in one box. And there's a even small one like this. Anyway, I'm not trying to sell any product here, but I'm trying to tell you there are a variety of selections, and sometimes they use refractive index, and they use all kinds of physical properties to create interferometer that can fit it in a certain system that you are trying to measure. So anyway, this is it, and I hope you like, and I'll see you later.